fellow embedded heads. In this video, I'm going to show you how you can visualize and analyze Zephyr applications on Arm Cortex-M based MCUs using SEGGER SystemView in combination with SEGGER debug and trace probes. If you're working with a different RTOS, this video will still give you a great introduction into SystemView and all its features. For links and hints, please see the description below. If you're enjoying this video, please like and subscribe. Let's get started. First, let's review what a typical Zephyr development environment looks like. Typically, you're developing your Zephyr application using some integrated development environment or via Microsoft Visual Studio Code with some specific extensions, or simply using the West Meta tool for Zephyr. Your Zephyr project most likely has a configuration file called prj.conf, which we're going to talk about in more detail later on. Whenever you build your Zephyr code, you're invoking a toolchain of your choice that supports your target MCU. This typically results in an executable ELF file that also includes all required debug information. You can then open that ELF file with SEGGER Ozone and debug or trace your project on your target board using a SEGGER J-Link or J-Trace probe, as shown in a separate embedded head video. But in addition to that, you can also visualize and analyze your Zephyr application using SEGGER SystemView. Note that you don't need to use Ozone for this. You can use your development environment to flash the target board with your application using your J-Link. SystemView is an analysis tool from SEGGER that records, visualizes, and analyzes event data captured on your embedded system in real time. It uses the existing J-Link debug connection, for example SWD or JTAG, in combination with SEGGER Real-Time Transfer, or RTT for short. No additional pins are required. SystemView does require some instrumentation in the code. However, the good news is that the Zephyr kernel already includes the required instrumentation. This means that no changes to your Zephyr applications are necessary in order to use SystemView. You can find out more about SystemView on the SEGGER website. You can also download SystemView from there. Under SEGGER's friendly license, you can use SystemView free of charge for evaluation or non-commercial purposes. In order to visualize and analyze Zephyr RTOS applications with SystemView, it is important to add a few Kconfig settings to the configuration file in your Zephyr project. With these settings, SystemView can work with Zephyr-based applications. For this tutorial video, I'm using an NXP MCXN947 Freedom Board that is connected to my PC via a SEGGER J-Link. As my Zephyr development environment, I'm using the NXP MCUXpresso extension for VS Code, and I'll be working with the threads example from the Zephyr repository. After updating your project configuration file as mentioned earlier, rebuild your Zephyr project in whatever development environment you're working with. Then flash your target board with the updated executable, for example via the Flash programmer built into the NXP MCUXpresso extension for VS Code. Now open SystemView and configure the recorder configuration. J-Link is what you're using, so click OK. In the target connection settings, select the MCU on your target board. In my case, this is the NXP MCXN947, CPU 0 of that device, to be exact. Select your target interface, interface speed, and number of cores. You may also need to set the address of the RTT control block manually to make sure SystemView can find the RTT control block. You can look for symbol _SEGGER_RTT in your map file. Since that address can change as you work on your Zephyr project, it's actually better to specify an address range. Now that the recorder configuration is all set, you can start the SystemView recording. SystemView instructs the connected J-Link or J-Trace probe to connect to the target device via the selected target interface and start the application. You can now see exactly what's happening in your target application in real time as it is executing. SystemView essentially works like a logic analyzer for your embedded system. You can zoom in and out in the timeline window trigger on different conditions for tasks, interrupts, or markers, and get vital context statistics, all while your application is running. Let's take a tour of the various windows in SystemView as it is recording. The Events List window shows all events as they are reported by your application and displays their information, such as an ID to locate events in the list, a timestamp selectable to be shown either in target time or recording time, the active context, meaning the task, interrupt service routine, etc., which was executing, an event description displayed with the type of event, for example, interrupt service routine entries and exits, task activity, or API calls, any resources that are associated with the event, and the event details describing the parameters of the event, for example, the API call parameters or runtime information. For multi-core recordings, the events of each core are displayed in a separate events list. When starting or loading a recording, a corresponding number of events lists are opened automatically. The timeline window visualizes all events that are being recorded in the events list. It shows the system activity in your application over time by context items that were active in your application since the recording started. For example, one context item is interrupt service routine number 15, which is the Cortex-M SysTick interrupt. This Zephyr application also has 3 threads, blink 0, blink 1, and UART-out. Plus, we have the RTOS scheduler as well as the idle thread. For multi-core recordings, the context items are grouped by cores. Individual cores can be hidden via the checkboxes above the timeline. We'll come back to the timeline window later on after we stop the recording. The CPU load window is showing the time frame displayed in the timeline window divided into a configurable number of bins. Each bin acts like a bar graph, showing the CPU load distribution for each context item during the time representing the width of the bin. For example, during this section of the timeline, the CPU is 100% busy executing the UART-out thread. The Contexts window shows statistical information for each reported context item, such as the context item's name and type, including the priority for tasks and the ID for interrupts, the core associated with the context item, stack information for tasks or threads, the number of activations of the context item, the CPU load, meaning the ratio of the context item's active time to the overall recorded time, the total runtime, meaning the total time the context item was active, the time interrupted, meaning the total time the context item was suspended by interrupts, the last, min, and max runtime, meaning the duration of the most recent, the shortest, and the longest time the context item was active, plus some more. The runtime window helps to identify the spread and potential outliers for the runtimes of each context item by showing the following statistical measurements: the minimum or shortest runtime, the first quartile runtime, the median runtime, the third quartile runtime, and the maximum or longest runtime. These statistics can also be visualized as a box plot displaying the distribution, center, and spread of the recorded runtime values for each context item. This provides you with a visual indication of how stable your application is. By default, the histogram of the recorded runtime duration samples always consists of 100 bins for each context item. Notice that the Zephyr idle thread has no runtime information, because it only has one activation that just gets interrupted by the other context items. The System window displays information about the target system as reported by the application, like the application name, the running OS, information about the target hardware, and timing information, recording information like number of events, the average and peak event frequency, and additional user-provided metadata about the recording, statistical information about the analysis phase of the recording, and statistics about tasks, threads, interrupts, timers, and other SystemView events, such as task switches and interrupt frequency, which provide a quick overview of the system. The properties and metadata are saved with the recording and allow identification and preset configuration of a recording for later analysis. All entries are grouped by the respective core. The Zephyr Threads example application doesn't make use of these features, but the terminal window can show printf output from the target application, and the heap window can display allocations and deallocations of dynamic memory recorded using heap-related API functions. Let's stop the recording now. You can zoom out to get a bird's eye view of the recording. This also lets you see the changes of the data in the data plot window over time more easily. The data plot window visualizes user-defined data over time. In this case, I modified the Zephyr Threads example to periodically send the value of the count variable to SystemView to be displayed in the data plot window. The data plot window is synchronized with the timeline window, so you can see the correlation between the data and the Zephyr threads being executed. The corresponding events are also shown in the events list. You can zoom back in to get an understanding of the frequency with which things are happening. In this example, you can see that there is CPU activity every 100 milliseconds, apparently to send data via the UART performed by the UART-out thread. You can further zoom into any point of the recording to do more analysis of the sequence and timing of the recorded events. On further inspection, you can see that the systig interrupt fires every 100 milliseconds, and it is actually the blink 0 thread that runs first, before the UART-out thread. At this point, it is important to know that Zephyr is a tickless RTOS by default, which means the kernel tries to avoid generating periodic interrupts when the system is idle or all threads are sleeping for long duration. When the system is idle, the systig is reprogrammed to fire at the exact time the next kernel event, for example a thread's timeout expiration, is scheduled to occur. This allows the CPU to enter low-power sleep modes for longer periods, consuming less energy. The systig interrupt then serves as the wake-up event, at which point the kernel wakes up and performs necessary scheduling decisions. We can see such a wake-up event right here. The systig interrupt is firing, interrupting the idle thread. We can see the reason for this. The blink 0 thread is ready to run again, presumably because its timeout has expired. We can use the arrow down key to look at the events that happen next. After the systig interrupt exits, the idle thread gets suspended, and the scheduler runs the blink 0 thread, making it the current thread. Blink 0 returns from its 100 millisecond sleep, performs some work, and then sends a data sample of the counter variable over to SystemView. After doing some more work, presumably blinking one of the LEDs on the board, blink 0 then calls the Zephyr API functions kFIFO-put and kQappend, which gets the UART-out thread marked as ready to run next. After kQappend and kFIFO-put both return, blink 0 calls ksleep in order to put itself to sleep for another 100 milliseconds, allowing the scheduler to run UART-out and make it the current thread. UART-out makes a series of system calls, most likely to send individual characters out via the UART. After UART-out is done, it gets blocked, and since no other threads are ready to run, the scheduler sends the system back to the idle thread. But you can tell that sometimes something else is going on. Right here, the systig interrupt fires in the middle of UART-out because the blink 1 thread wants to run. After UART-out is finished, the scheduler runs blink 1, which is returning from its 1000 millisecond sleep. Blink 1 performs some work, and then, just like blink 0, sends a data sample of the counter variable over to SystemView. After doing some more work, presumably blinking one of the other LEDs on the board, Blink 1 itself then gets the UART-out thread marked as ready to run next. Blink 1 calls ksleep in order to put itself to sleep for another 1000 milliseconds, allowing the scheduler to run UART-out and make it the current thread. UART-out sends more characters out via the UART and then gets blocked. Again, since no other threads are ready to run, the scheduler sends the system back to the idle thread. As you can see, SystemView offers deep insights into the runtime behavior of your system, surpassing the capabilities of traditional debuggers. SystemView can help you ensure your system performs as intended, identify inefficiencies, and uncover unintended interactions or resource conflicts, especially for complex systems with multiple threads and interrupts. You can save the recording to a file for analysis at a later time or for documentation of the system. And there you have it, fellow embedded heads. Now you know how to visualize and analyze your Zephyr applications using SEGGER SystemView in combination with SEGGER J-Link and JTrace probes. If you enjoyed this video, please like and subscribe. Please also feel free to leave comments below. Thanks for watching.